Good morning, everyone. Reed here. I got some of my team here, and I have a call that should be coming in now around the same time I'll be doing this podcast. So I may have to put the call on mute for a minute to take a phone call. I got a peer-to-peer to do. Stuff's never ending. Um, so today we're going to go through the norepinephrine molecule in the norepinephrine receptor. Remember, um, it's very important to know these receptors because it's important to know where they're located, what type of receptors they are, and basically how they work, how they operate. Let's see. Okay, so here I'm going to let me go here. Okay. So here, great. Okay, let's see here. Explain the norepinephrine receptor. Okay. So remember, when uh, when you're interviewing a patient or you listen to someone and they're in a certain type of distress, hold on one second. Okay, back here I'm back return, folks. Okay, so let's see here. So we're going to go over this norepinephrine here. Let's see. Okay, let's see here. Okay. Right. Okay. So remember, each neurotransmitter has sort of a different theme associated with it. Remember, dopamine, elevated levels of dopamines are typically associated with stories similar to horror movies. The person's behind me, or the person's scared, or I'm apprehensive, paranoia, things like that. Remember the elevated serotonin story is one of falling in love, right? And feeling very happy and enthusiastic, and decreased serotonin levels, simply similar to the symptoms of depression, right? So you can see how the neurotransmitter itself has a certain theme that goes along to it. Someone comes in with a depression, thinks primarily of serotonin, even though the other receptors can be involved. Neurotransmitters can be involved. But what about norepinephrine? Elevated levels of norepinephrine are typically associated with symptoms we would call consistent with mania, right? And so this is at the end of the Super Bowl, when they run up to the quarterback and say, "Hey, you just won the Super Bowl. Where are you going?" They say, "I'm going to Disney World." That's norepinephrine, right? And that's like mania. And so we're going to go look at the norepinephrine receptors and the molecules. So elevated levels associated with like elevated manic symptoms and things like that, and lower levels, diminished levels associated with symptoms consistent with depression. So let's see how this works here. So norepinephrine receptors, also known as adrenergic receptors. Remember, the adrenergic nervous system, sympathetic nervous system, are proteins on cell surfaces that bind to the neurotransmitter norepinephrine, triggering a variety of physiological responses like increased alertness, blood vessel constriction, and heart rate changes. There are two types of main family: alpha adrenergic receptors, all right, A1 and A2, and beta adrenergic receptors, beta 1, 2, 3, each with different cellular effects and function in the body for fight or flight responses. So remember, norepinephrine, adrenergic system, flight or flight, sympathetic nervous system, right? So let's look at the norepinephrine receptor. Okay. Binding norepinephrine is released into the synaptic cleft, that is the space between the cells, right? It then binds to a specific adrenergic receptor on the surface of the cell. Okay. There's a G protein coupled receptors. So there it is. Noradrenergic and norepinephrine receptors are G proteins, remember? The G proteins are connected to that signal transduction cascade. And that's how you order a specific product from the cell body, and the cell body produces something. And remember, it takes time for that factory to receive that message, process the request, and send out a product. And so norepinephrine is G protein receptors, as opposed to ion or ligand-gated receptors. Here, the effect, this signaling cascade ultimately alters the cell's activity, leading to either an excitatory or inhibitory response, depending on the response type of the receptors. So remember, the alpha and then the beta. So we're going to see those. I'm sure we're going to see those types later. Okay, so depending on the receptors, alpha receptors, beta receptors. Okay, types of alpha receptors. Okay. Alpha receptors typically have excitatory effects. Okay. All right. Alpha 2 receptors can have an inhibitory effect. Okay, inhibitory. Okay, let me see about the beta. They're found in the heart and kidneys. Increase. Okay. Okay. The betas involved in processing bronchodilations. Okay. So beta ones, heart and kidneys. Beta twos, bronchodilation. Okay. Beta threes, finally found primarily found in adipose tissue. Okay. Hmm. Norepinephrine receptors in adipose tissues. First time I thought about that. I can see in bronchodilation, you know, you need to increase your respiratory respiration. I can see in your heart rate, you know, blood flow and kidneys cleaning the blood. Okay. So alpha 1s typically have excitatory effects causing smooth muscles and the blood vessels to contract. Yep, there's alpha 1 receptors. Yep. Remember, alpha 1, I think it's the same as alpha. Is this the same as alpha 1 adrenergic blocker? It's the same thing as norepinephrine one here. Anyway, alpha 2 can have inhibitory effects, but also located presynaptically, meaning they can reduce the amount of norepinephrine released from the neuron itself. So the alpha 2s are located presynaptically. Beta receptors. Okay, they found in the heart and kidney and may increase heart rate and contraction and stimulate the release of renin, which help regulate blood pressure. Oh, okay. So norepinephrine increases renin through the beta receptors. Oh, wow. Okay. Remember beta blockers, right? Slow it down. Beta blockers block the beta, decrease the. Now this is like this is where psych is meeting cardiology right here. The beta blockers block it, decreasing renin angiotensin system right there. The renin. Okay, beta 2 involved in processes like bronchodilation in the lungs and relaxation of smooth muscles. Okay, beta 3 located in adipose tissue and involved in a process related to metabolism. I guess if you need more energy, yeah, that makes sense. Yeah, the receptors are located everywhere we need to get up and go, right? On your heart, your blood vessels, your lungs, the energy source. Okay, great. Fight or flight response. Norepinephrine receptors are central to the body's response to stress, preparing the body for intense physical activity. In the brain, the role plays in alertness, arousal, and attention. Right? Diseases malfunction in the noradrenergic system, and thus its receptors have been linked to conditions such as depression, anxiety, and ADHD. Okay, so that's interesting. Now, so we went through G proteins and things like that. So I don't think I needed to go through those. And let me look at the what networks. Let me see what networks are primarily regulated by norepinephrine. Let me see that. Let's see here. Okay. Look, norepinephrine producing neurons, mainly from here and other brainstem nuclei innervated nearly all regions of the brain cell and spinal cord, all of them. And they have especially dense projections in the cerebral cortex, cerebral cortex, hippocampus, right? The amygdala, the cerebellum. We went through the hippocampus, we went through the amygdala. We really didn't go through the cerebral cortex. We went through parts of it. Didn't go through the cerebellum yet. These projections via the dorsal and ventral noradrenergic bundles enable norepinephrine to modulate a wide range of function, including arousal, attention, mood, memory, and response. Okay, so these projections allow cerebral cortex and play a role in cognition and attention and concentration. That's why the medications for attention and concentration disorder and hypoactivities are things like Wellbutrin that targets norepinephrine and dopamine. Also, the stimulants also target release of norepinephrine also. Hippocampus, All right. Critical for learning and memory. The cerebellum, um, motor control and other functioning. The amygdala, look, mood and emotional processing. See norepinephrine, yeah. Hypothalamus. Okay, innervates the hypothalamus, regulates physiological process, including appetite and stress regulation, changes in weight and appetite, and ability to handle stress. Spinal cords, projection from the DNB and VND, okay, in the spinal cord. Okay, great. And I think that's all I wanted to go through for now. Okay, and so I think that's all I'll do for today. We're at 15 minutes. And let me see if I have any questions real quick. So let's see here. Hey, Max, how's it going? Thanks for the question, Max. Let's see. Can lifestyle change naturally regulate norepinephrine levels in the brain? I think lifestyle changes that promote more integration with the environment, right? So if you're getting more exposure to the sun, you know what I'm saying? If you get more exposure to the beach, if you get a chance to lay in the sand more, if you get a chance to do healthier activities, I think those things, they have the environment have more of an opportunity to sort of increase your norepinephrine levels on its own if you get exposure to those things. And so I think, getting reintegrated into the environment and things like that would be very helpful for you. Great. Thanks for the question, buddy. Okay. Why is norepinephrine key to attention, focus, and concentration? Noradrenergic, the system, right? It's your fight or flight. This is the system that primarily results in activation, and it primarily activates the areas that's responsible for arousal, attention, and concentration. In memory, let me show you. Let me see if I can give you an idea. Okay, let me see this. Okay. So here is the mesocortical pathway right here. All right. Here's the mesolimbic pathway. This mesolimbic pathway is the pathway that's primarily targeted for drugs of abuse or reward. And so hyperactivity or increased activity in this mesolimbic pathway typically results in increased awareness, increased alertness, improved attention and concentration and things like that, right? And that process of here is also it's mediated with by dopamine, glutamate, but also norepinephrine on this network too. Same thing here with this pathway here, this huge pathway. This area over here is where the hippocampus is. This is where we get the memory improvements and things like that with increased norepinephrine activity. And over in this region here, this is more where the prefrontal cortex is. This is where we sort of process things for abstract reasoning, right? Damage to the fibers in this area typically produces deficits in executive functioning skills, reasoning skills, and so the person may tend to be more concrete. Okay, and as we go over here to the frontal lobe damage here results in executive functioning difficulties, poor attention, poor concentration, poor organization, poor planning, poor multitasking, poor sequencing, difficulty with divided attention. And so they will need a stimulant, right? The stimulant stimulates the activity in this part of the brain. And so the brain processes more information. So the stimulants increase the network activity. The network activity processes more information. And so and the person becomes more aroused. So that's why we want to stimulate the brain in attention deficit hyperactivity disorder, and the stimulation of the frontal lobe gives them more executive functioning control. Therefore, it can shut down the impulsive and unfiltered body movements, right? So it's sort of like a oxymoron. If someone's hyperactive, why would you give them a stimulant? We want to stimulate the frontal lobe, and the more functioning mature the frontal lobe is, the more the person will be able to have control of themselves. Hope that was helpful for you guys. Okay. Let's say here. Hey, hi, Ahash. How's it going, buddy? What role does it play in ADHD and attention disorders? Yeah, like I was saying, hypoactivity. If you were to take a scan of the brain and looked at how much sugar each part metabolized, then you'll get an idea of how active that part of the brain is. It just so happens that in the case of ADHD, this frontal lobe area here is hypoactive. That's because the networking is hypoactive. So what we want to do is we want to block the norepinephrine reuptake pump on the presynaptic receptor. And that will increase the titer of norepinephrine in the synaptic cleft. And with this happening, but at the junction of almost all the nerve cells in that region, it will increase transmission across that network, and we'll get an increased noradrenergic response, noradrenergic hyperactivity. You'll process more information about what's coming in, and hopefully the person will be able to plan, organize, and sequence their tasks good enough so they don't be irritable or too active, out of place with the people around them. Makes sense? Thanks for the question. Okay. Thank you so much, Current Issues. Appreciate your question. David Woods. Hey, Dave. How's it going, buddy? What are the most common drugs of use that you see affects that system? You see here, this mesolimbic pathway here is a highly dopaminergic pathway too, in addition to serotonin also. And so it's this pathway that's affected in things like cocaine use, LSD, PCP, also ecstasy. So what are the common drugs of abuse? I think this is the target, and the drugs of abuse typically target dopamine and or norepinephrine. Okay. All right. So I think that's it for today. I don't want to go too long, but if you have any other questions, please feel free to like, subscribe, and share. If you have any other questions, you can please leave them here. I'll see if I can get back to them. Otherwise, I think that's it for me. I'll see you guys later. You guys have a nice day, guys. Take care.